Hey guys, welcome back to my 4-part series on quantum mechanics. This is part 2, and if you guys haven't seen the first part yet, please check that out because without that you'll be kind of lost in this one, so I highly recommend you do that first. Now, before we start, it's important to know what modern physics is actually composed of before we get into the details of it. Now, modern physics is made up of 2 parts. One is quantum theory and one is the theory of general relativity. Now, general relativity deals with our universe on a larger scale. So black holes, planets, gravity, all these big things and how they work. Whereas quantum theory is the exact opposite of that. It deals with everything on a subatomic level. So very small stuff. Now, in today's video, I'll be discussing quantum theory and its features such as wave-particle duality, Schrodinger's cat, and a bunch of other different parts of it, right? And tomorrow, I'll be doing a video on relativity, so please keep an eye out for that, and let's get into it. Now, to understand quantum mechanics, we're going to be looking at a bunch of old dead dudes and their work. Starting with this guy from France called Pierre-Simon Laplace. Now, this guy believed that if we knew the position and the momentum of a particle, we could predict its future. He also believed that one day humans will discover a set of laws that will allow us to predict everything that will happen in our universe, including human behavior. Now, fast forward to the 20th century and Mr. Werner Heisenberg is born. Now, this guy discovered the one thing needed to disprove Laplace's theory of determinism, which this thing was known as the uncertainty principle. But what exactly is the uncertainty principle? Well, the uncertainty principle states that both the position and momentum of any given particle cannot be measured accurately at the same time. And why is that? Because if we want to measure the position of a particle accurately, we would have to disturb its momentum. And say if we want to measure the momentum accurately, we would have to disturb its position. So either way, we cannot measure both characteristics of a particle accurately. By figuring out this entire principle, we were able to prove that Laplace's theory of the world being deterministic is actually not possible. Nowadays, Heisenberg's uncertainty principle has become the basis of modern quantum mechanics. But you might be wondering, how exactly does it play a role in our lives? Like, there's not much uncertainty about anything in our lives. Say a bottle is on a table. You know it's on a table because it's there, you can see it, right? Unless you hit it off the table, then you don't know where it might fall. But when it's on the table, it's on the table. You know that for sure. So where exactly does this uncertainty actually come into play? Well, before we get into that, we have to understand what wave theory is and what are the characteristics of both particles and waves. So, what exactly is a particle? Well, when it comes to particles, you know its position at any possible given moment. You are 100% sure of its position and you know exactly where it is. Waves, on the other hand, aren't so simple. Waves are periodic disturbances or oscillations that spread out in space. It could be described by a ripple in a pond or a slinky even. But the difficult part about waves is that you are never 100% certain about its position because of the fact that it's spread out over time. Now, the interesting thing about quantum mechanics is that waves are actually particles. Now, a wave may behave like a particle in certain conditions, and a particle may behave like a wave in certain conditions. It's confusing, I know, and while it may be difficult to visualize it, the double-slit experiment does a really good job of explaining it and also proving how this is actually possible. Okay, so in a double-slit experiment, there are 2 slits in a wall, and a wave is being oscillated on one side. The wave will eventually travel through the gap and both waves will diffract. This will create what's known as an interference pattern. The fun part about this is that if we send particles instead of the wave through the 2 slits as well, the same interference pattern shows up, even if the particles are sent one by one through each of the slits. What this eventually led scientists to believe was that each particle has its own wave function. A particle will have wave-like characteristics and behave like a wave until it is observed on the other end of the 2 slits. During the time from when it is released to when it is detected, the particle is thought to be in a quantum state or a superposition when it's both a wave and a particle at the same time. Now, getting back to the uncertainty principle, how does all of this nonsense of a wave and a particle connect back to that principle? Now, if we can determine the wavelength of any wave, we can determine what its momentum is going to be, but we still don't know its position. Whereas on the other hand, we have a particle whose position we're 100% certain of, but we don't know its momentum. So how do we get around this? Well, in order to do that, we need to combine both objects to create what's known as a quantum object, as I explained before. We need something that's both a wave and a particle, so we can figure out the momentum and the position of the object. So how exactly do we achieve that? Well, we can combine different waves. Now what happens is that the peaks and the troughs of the two waves should be the same at some points and while different at the others. In some places, the wave would cancel out and become flat, whereas in other sections, the peaks would increase. If we keep doing this, we would eventually form a small enough wave packet in which we see a single wavelength. By doing this, we've created a quantum object, an object which has both particle and wave-like characteristics. However, by doing so, we've become uncertain of both the position and the momentum of the object. The position of the particle isn't restricted to a single point, but there are different levels of possibilities of finding it within a certain section of the wave packet. But there is no 100% certainty. As for the momentum, we are uncertain of that because we found this wave packet by combining different waves. So the momentum of the particle could in theory belong to any of those waves. Now, if we want to decrease the uncertainty of the position of the particle, we would have to keep adding more waves to decrease the size of the wave packet. But in doing so, we're becoming more uncertain of the momentum of the particle because there's more waves to choose from. And if we try to decrease the uncertainty of the momentum of the particle, then we would have to use less waves. That means our wave packet would be bigger. And if the wave packet is bigger, that means the uncertainty of the position goes up. And this, in a nutshell, is the uncertainty principle. And it's represented by this equation. The uncertainty in the position of the particle multiplied by the uncertainty in the momentum of the particle will always be greater than or equal to Planck's constant divided by 4 pi. Now this probably makes no sense to you right now, so I'll break it down for you. We've already discussed the two uncertainties on the left-hand side of the inequality. If the uncertainty of the position goes down, then the uncertainty in the momentum will go up in order to maintain the inequality. As for the right-hand side, all you need to know is that Planck's constant is a very small number discovered by another old dead dude. It's so small that in most everyday situations it doesn't even come into play. It's only when we look at very small objects, such as the subatomic particles that make up an atom, when this constant and the entire inequality actually comes into play. This is because large objects have a very short wavelength, because they have high momentum. The greater the momentum, the shorter the wavelength. It's actually so short that you can't even measure it directly. But when you look at subatomic particles, the wavelength becomes big enough that the uncertainty principle actually comes into play. Now I know that was a lot of information to grasp in a really short amount of time, so let's take a break and do something fun, shall we? Now, everyone loves cats and kittens, right? So how about we just watch a couple of those for a second or two? Now, the reason I showed you those cats was because cats also play a role in quantum mechanics. But how does that exactly work? Okay, now another old dead dude from the 20th century, Schrodinger, came up with a thought experiment. It was originally used to disprove the idea of quantum mechanics and show how absurd and weird it was, that it wasn't really possible. But nowadays, it's used as an explanation for the theory. It's used to explain the theory to people who aren't really familiar with it. Now, what this experiment was, basically a cat is placed in a box with a poison vial. There's also this radioactive atom that's present there. So if the atom decays, the poison vial breaks and the cat dies. But if it doesn't decay, the poison vial doesn't break and the cat doesn't die. And this decay or not decay state is completely random. There's no way of predicting whether it will decay or not decay. So the chances of this happening are completely random. The box is closed and left for 1 hour, after which the cat will either be alive or dead, but we don't know. But before you open the box, quantum physics states that the cat is both alive and dead at the same time. This is essentially the same thing as the wave-particle duality we discussed earlier, how the particle can be both a wave and a particle at the same time. And this is what's known as a superposition. Now, Schrodinger also came up with another thing called a wave function. Now, we discussed that particles can behave like waves, but how do we calculate or measure those characteristics of that wave? Well, we use what's known as the Schrodinger wave equation, which is this, or the wave function. Now, this mathematical randomness probably doesn't make any sense to you, so I'll simplify it and shorten it down, and I'll tell you what the most important part about this. Now, the most important thing about a wave function is what it represents. Now, we discussed earlier that a wave packet of any quantum system includes all the possibilities of the position of the particle. But the wave function itself is a mathematical representation of those possibilities. It tells us exactly what the probability of finding that particle in a certain area of the wave packet is. But the interesting thing about these wave functions are that if a measurement is made, the wave function is no longer a number of possibilities. but rather the entire function collapses and the particle is found at a single point. Now this wave function can also be used to describe any quantum system. So this cat experiment has many quantum systems in it. The cat alive and dead is one quantum system. The vial broken and not broken is another. And the atom decayed or not decayed is another. Now instead of saying that we have 3 or 4 different individual quantum systems, we say that these quantum systems are entangled. They all rely on one factor, which is whether or not the atom decayed or not. And this entangled quantum system can be described by a single wave function. This wave function will collapse once we open the box and we make a measurement, observing what the state of the cat is. But when we open the box, we don't see all the different possibilities. We only see one thing. We only see one outcome. This is what happens in real life, or at least in our reality. Yeah, that's right. What if I told you that out there's possibly an infinite number of realities, or an infinite number of universes? Well, how is that even possible? Well, let's just say that instead, when you open the box, you're not making a measurement, but rather you get entangled with the previous systems. So you yourself are in a quantum state. You've seen the cat alive, and you've also seen the cat dead. Now, the way that that's possible is that the universe actually splits. In one reality, you'll be seeing it alive, and in one you'll be seeing it dead. So they both start off at the same point, but when you open the box, get entangled, the universe splits into 2. This entire theory is what's known as the multiverse theory. However interesting it may be, it's almost impossible to prove because the 2 realities, or the infinitely number of possible realities, none of them can interact with each other. They all exist in their own separate space-times, and they all exist in separate universes that can never interact with each other. So even if there are all these realities out there, you'll never be able to meet them or understand them or see them or do anything with them. But you guys might be wondering, I said infinite universes. Right now we only have 2, one where it's dead, one where the cat is dead, and one where the cat is alive. So how exactly are there infinite universes? Okay, I'm getting there, slow down guys. Now, the multiverse theory basically states that every time a quantum system gets entangled with another quantum system, the universe splits. And this whole Schrodinger cat experiment is only a single quantum system. But these systems, they exist all around us, inside our body, out in the environment, everywhere. They're literally everywhere. And if 2 or more of them were to interact with each other, the universe would literally split. Now it's actually impossible to say how many times the universe is actually split already and how many times it's actually going to split in the future. So we might as well just say that the number of universes is actually infinite. This theory also brings up Murphy's law, which states that anything that can happen will indeed happen. And if we look at it from a quantum perspective, we can say that everything happens, just not in the same universe. So the cat dies and stays alive, just in separate universes. It's crazy to think about how something that can happen on a subatomic level can affect the universe in such ways. These quantum laws can essentially say that there are infinite numbers of us, infinite numbers of you, infinite number of everything in the entire universe, or in the entire multiverse, I should say. Thank you guys so much for watching today's video, and I hope you understand everything. If you want further clarification, you want to research more, I've linked some videos down in the description below and you can check them out. They're made by different creators on the topics we talked about today. And if you really want to learn more, you can check those out. Now tomorrow's video is going to be about relativity and the space-time continuum, so please keep an eye out for that, and let me know what you guys thought about today's video in the comments below, and it'll really help me improve my filmmaking and video quality as well. Thanks, and I'll catch you in the next one.